Alright team, let's look at a Leetcode problem called valid anagram, right? Number 242. It's an easy problem. So you're given two strings, S and T, and your algorithm should return true if T is an anagram of S and false otherwise, right? If you don't know what an anagram means, they have given a nice definition here. An anagram is a word or phrase formed by rearranging the letters of a different word or phrase using all the original letters exactly once, right? So they have given two examples here. In first example, T is an anagram of S. So if you look carefully, there's there are three A's in S, there are three A's in T, there's one N in S, there's one N in T, there's one G in S, there's one G in T, there's one R in T as well, and there's one M in M. So T is an anagram of S. In second example, uh, T is not an anagram of S because T has C and there's no C in S, right? And they have given a bunch of constraints here. S and T, your inputs will at least have one letter in it, and at max it will have 5 to 10 raised to 4. And S and T consist of lowercase English letters. Okay, that's good, right? So let's go to the whiteboard next.
Let's look at a simple example here, right? Let's say we have two strings, S and T, and let's say S is equal to ABC and T is equal to ABCD, right? This is the simplest possible case. If S and T are not of the same size, right? Clearly, T is size 4, S is size 3. You can straight away return a false. You know the answer, right? There's no way on earth T is going to be a valid anagram of S, right? So this is the most basic case. If S and T are of not the same size, we know it's not, there's no way on earth it's going to be a valid anagram, right? But let's talk about a case where S and T are of the same size. So let's say S is ABC and T is CBA. How can we tell or how can we prove that T is an anagram of S? One easy way is to compare characters, right? You can compare each character in T with each character in S, and if there's a match, if all the characters in T match to all the characters in S, life is good, right? So let's walk through this. For every character in T, so first character is C. Is there a C in S? Yes, right? For second B, is there a B in S? Yes. For an A, is there an A in S? Yes. So T is a valid anagram of S, right? But there's a problem here. There's a big problem here, right? Let's say S is equal to ABC and T is equal to BBC, for example, right? If we go by our comparison algorithm, what will happen in this case? We'll say, okay, let's check B. Is B present in S? Yes. Is B present in S? Yes. Is C present in S? Yes. Oh, there you go. T is a valid anagram of S. But that's not true, right? There are two B's here and there's only one B here, right? And according to the definition, T cannot be an anagram of S, right? We can slightly improve this. How can we improve this, right? The easiest possible way to improve this is we can sort. We can sort both the strings, right? We can sort both S and T and then do a compare, right? That's slightly better. And that makes our algorithm kind of foolproof as well, right? So in this case, S is already sorted, T is already sorted, but the comparison is going to fail, right? S is not equal to T, and therefore therefore T is not an anagram of S, right? But let's look at another case. Let's say S is equal to, let's use something different, A, B, C, D this time, and let's say T is equal to D. Let's say T is equal to D, B, A, C, right? Let's say S and T are our input strings, and S is equal to A, B, C, D, T is equal to D, B, A, C. Now, the first step that we do is sort, right? So S is already sorted. When we sort T, it becomes A, B, C, D, right? And then if we do a compare, guess what? T is a valid anagram of S, right? So the brute force approach would be to sort both of your strings, both of your input strings, sort S and T, and then do a compare, right? That's the brute force approach. Now, if you think about it, the fastest sorting algorithm can give you a time complexity of n log n. So that would be your brute force time complexity. And I think the space is at least in C++, it's I think big O one. You end up using constant space. So the next question that the interviewer might ask you is, okay, can you do better than n log n? And your answer should be always yes. Just kidding. But yes, there is a better way to write this algorithm, right? And the answer here to how can you improve this algorithm lies in counting, right? So let's look at an example so that things become clear, right? So let's say S is A, B, C, D, and let's say T is equal to D, B, C, A, right? What if I count characters in S as well as in T, right? And if the counts, if T is an anagram of S, right, the counts should match, right? So for example, if there's one D in T, there should also be a one D in S, right? If there's one B in T, there should be one B in S. And if there's one C, there should be one C in S. If there's one A in T, there should be one A in S, right? Now we'll have to keep track of these counts, right? Once we start counting characters in, let's say, S, we'll have to keep a track of it. So let's use a map for now, right? And let's say our map, the key for the map is char, and the value can be int, right? So let's count all the characters in S and put it in the map, right? So S has a A, S has a B, S has a C, and S has a D, right? So this will be our map. Now, when you're counting characters in D, instead of adding like we did for S, let's subtract so that our life becomes easy, right? I'll tell you how. But let's subtract. So we found a D in T, so let's make this 0. We found a B in T, let's reduce the count here. We found a C in T, let's reduce the count here, and we found A in T. So in case if T is a perfect anagram of S, your map should have characters with all their counts equal to 0, right? So if there's any character in the map that has a non-zero count, guess what? T is not an anagram of S, right? And let's prove that with an example, right? Let's take the example that Leetcode gave us. So S equals to rat and T equals to car, right? We have a map of char and ints, right? Let's count characters in S, right? So we have 1 R, we have 1 A, and we have 1 T, right? And we said for each character in T, we are going to subtract 1, right? So we have a C here. Oh, guess what? There's no C, right? We have a A in T, we subtract it, subtract 1 from our A. We have an R, we subtract 1 from our R, right? And then when we check the map, guess what? We have a character with a non-zero count. That means T is not an anagram of S, right? So let's talk about improving this map solution a little bit, right? And I think we can do better than a map by using a array, right? So imagine you have an array of size 26, right? It starts from 0, ends at 25, and each possible slot in this array represents a character, right? So 0 represents A, 1 represents B, 2 represents C, and so on, and 25 represents Z, right? Now, the next challenge becomes, okay, how do we calculate the right indexes for our characters in our input string, right? So, for example, if let's say S is equal to R-A-T and T is equal to the example we saw earlier, so C-A-R, right? Now, when we are going over S one character at a time, how do we calculate the index for R? And if you think about it, you can do a simple subtraction here, right? Using the decimal ASCII value of R and A. How? Let's see it. So the decimal value, if you look up the ASCII table, the decimal value for R is lowercase r is 114, right? And the decimal value for A is 97, right? If you subtract 114 from 97, you get 17, right? So 114 minus 97 gives you 17. And this 17 becomes the index in your array, right? So if you want to update the value of R in your array, you subtract R's decimal value from A's, and that way you get the index, right? So here we write a 1, right? We do the same thing for A. Now in case of A, it's much easier, right? A's value is 97, and we're subtracting it from A, which is 97. So 97 minus 97 becomes 0, and we update the value of 0 here to 1, right? Now let's do it for a T, right? The decimal, if you look up the ASCII table, the decimal value for T is 116, right? So let's use space here. T is 116 and A is 97, right? And if you subtract 116 minus 97, you get 19, right? And that becomes your index for T. So let's say this is a 19 slot, we update this to 1. We do the same thing for T, right? We calculate the index for C, and this time instead of adding, we subtract, right? So C's value is decimal value is 99, right? And if we subtract 99, if you subtract 97 from 99, which is A's value, we get 2, right? So this value initially will be 0, and this, if you subtract, it will become minus 1, right? Because there was no C in S, this value wasn't updated, and if we subtract 1 from 0, we get a minus 1, right? Then we look at A, right? A's value we know is 0, so, and we had an A in S, so this becomes a 0, and R, right? R's value we know is 17, so we subtract 1 from here. Now if you think about it, every position in the array apart from C is going to be 0, right? And if we have any non-zero value in the array, that means T is not a valid anagram of S, right? Let's look at a happy example and let's simplify a little bit. So let's say S is A, B, C, and let's say T is CBA, right? That simplifies the array a bit as well. So let's say 0, 1, 2, 10, 10, 10, 25, right? Now let's go over S, and the default values in this array are all going to be zeros, right? So first we look at A, right? And A's calculation is going to be 97 minus 97, 0. So we update the 0th position. B's calculation is going to be, B's value is 98, so we subtract 97 from it, we get a 1, that becomes our index, and we update it here, so 1. And then C's value is going to become 99 minus 97, 2. So we update a value 2, update the index 2 here to 1, right? Now comes time to look at T, right? C's value we know is 2, so we subtract 1 from here, this becomes a 0 again. B is at index 1, so we subtract a 1 from here, it becomes 0 again, and A is at index 0, subtract 1. So now if you look at the array as a whole, every value is a non-zero value, meaning T is an anagram of S. Boom. Okay, let's dive into code next.
Alright team, enough talking, let's write some code. So let's go with the array solution that we just discussed. And the very first thing we said we are going to do is check the sizes, right? So if s dot size is not equal to t dot size, we know that there's no way on earth that t is going to be an anagram of s, right? So we can straight away return a false here. No need to do anything further. But if s and t are of same sizes, right? We said we are going to use an array of ints, and we are going to have 26 possible slots representing each letter, right, A to Z. And let's call this cache, right? Then we can go over the strings, right, the input strings one at a time. And for S we said we are going to add 1 to the slot, and for T we are going to reduce 1 from the slot, right, from the right index. So let's go over S int I equals 0, I less than S dot size plus plus I, right? And the way we are going to do it is we said we are going to subtract the decimal values of the characters, right? Look up the ASCII table, you will find the values. But here we are going to do S of I minus A, right? For S we are going to do this, and we said we're going to add 1 to the slot, right? So we can do plus equals 1, and the equation for T becomes very similar. So instead of S we use a T, and then instead of adding we subtract 1, right? So that way guys, we fill up the cache, right? We said that if all the values in this cache at the end are non-zero, or not all the values, sorry, if any value in the cache is non-zero, that means T can never be a anagram of S. But if all the values in S in cache are 0, that means T is a anagram of S, right? So next let's check that. So for all the values in the cache, we can use const auto ref c for all the values in cache. If a value is not equal to 0, we can return a false, right? This meaning T is not an anagram of S, right? But if we never hit this if block, that means all the values are in the cache are equal to 0, we can return a true, right? So let's run this. Oh, we got a compiler error here. Oh, I forgot a semicolon. Great. Alright, so accepted. All the test cases are good. Let's try to submit this. There you go. Beats 100%. Right? So hopefully guys you enjoyed this video. If you did, please leave a like and please leave your feedback in the comment section. Alright, thank you very much.